Okay, good morning, everyone.
Which one's the other?
I'm John Bowers, Director of the Institute for Energy Efficiency at UCSB. And on behalf of Novum at UCSB, I want to welcome you to this important forum on natural gas, the important topic for our whole country and for the world. This meeting was organized by Novum, a nonprofit formed in 2007. It started at UCSB when Michael Ditmore and Jim Knight were at a meeting of CAFLE and discussing convening physicists to solve the problem of climate modeling. And David Gross, the director of KITP at the time, suggested expanding the focus to something much more important about namely climate change. And his suggestion was that someone should find a way to explain these kinds of scientific issues to the general public. The need for countering anti-science and misinformation is never been greater than it is today, so Novum plays a very important role there. Novum was formed as a nonprofit to enlighten the discussion of subjects from geoengineering, the atmosphere, to nuclear power. And again, Michael Ditmore and Jim Knight were key to that, and I want to introduce Michael Ditmore to kick this forum off. He's an engineer and graduate of the Stanford Business School. He's been in Santa Barbara for 45 years and started multiple companies and 2 nonprofits. So please welcome Michael Ditmore.
Thank you, John. And good morning, everyone. Those here and those online that didn't want to brave the parking system at UCSB. CH4, methane, natural gas, has heated the homes in California and warmed our hot water for over 200 years. Initially, it was just for lighting. But we now know that methane is a potent greenhouse gas and many times more impactful than CO2. In 2014, Novum published in Science magazine the results of a year-long study on methane leakage. And one of our partners in that study was the Environmental Defense Fund, a speaker from whom you'll hear from in just a minute. 5 years later, the city of Berkeley passed an ordinance banning all new hookups, residential and commercial, for natural gas. A year later, Santa Barbara did the same thing, only exempting commercial kitchens, as I understand it. That was in January of 2022. This last spring, as a result of a lawsuit brought by the Restaurant Corporation, or the Restaurant Association of America, the Ninth Circuit Court of Appeals overturned the ordinances, saying there was a conflict with federal regulation and the federal regulation preempted the state. Berkeley subsequently, and Santa Barbara as well, withdrew their ordinances. They're on the shelf, as I understand it, at the moment, but we may hear some more about that as well. Today's forum is meant to educate, not to advocate. Novum is devoted to trying to bring more civil conversation about having to do with topics that we all like to fight about more than anything else, climate change being one of them. But we've done things as diverse as public employee pension funds, as John said, nuclear power, and so on. At the conclusion of the presentations, we have 6 experts today to talk, 3 here on stage and 3 via Zoom. At the end of those, we will take some questions, and you can submit those by text if you're in the audience, or you can also do it via chat on the Zoom connection. So without any further ado, I'm going to move our program over to our first speaker, who is Ramon Alvarez. Ramon is in Austin, Texas, and is the Associate Chief Scientist for the Environmental Defense Fund. And the EDF is very big on methane monitoring. In fact, Ramon may mention it, but they launched a satellite this summer from Vandenberg specifically to look at methane levels around the world. I'm going to turn it over right now to Ramon, and welcome to the Natural Gas Forum.
Good morning to everybody, and thank you for the invitation to speak today.
I'm going to speak about natural gas sort of from the context of climate and air quality. I'm going to be sharing some relevant science. There's been a lot of work in the last 10 to 15 years. I'm going to try to work through it slowly and sort of avoid going into the weeds, just to give you sort of some highlights and some considerations at the end about paths forward. About 25% of global warming caused by humans comes from methane emissions. And methane is the prime constituent of natural gas, typically 95% or so at the residential or commercial locations. The largest source of industrial methane emissions in the United States is the oil and gas industry. And so it's an important source that we need to pay attention to. And I want to talk first about methane emissions and how they are affecting the climate in a way distinct from carbon. Typically, you hear about carbon emissions, and that's really carbon dioxide. Carbon dioxide emissions into the atmosphere are going to determine how high the temperatures eventually get on the climate. Pollutants like methane are called short-lived climate forcers. They're short-lived because they're removed from the atmosphere in timeframes of a few years to a decade. Carbon dioxide, on the other hand, can last for centuries in the atmosphere. However, while these short-lived climate pollutants reside in the atmosphere, they can do a lot of damage because pound for pound, they absorb much more heat than carbon dioxide does. In the case of methane, it's about 30 times more on a 100-year basis. And on a shorter time frame, while it's still in the atmosphere, it's really doing damage about 80 times pound for pound than what carbon dioxide does. Other short-lived climate forces of importance include ozone and black carbon and hydrofluorocarbons. And the main thing is that while these are there, they are warming, but they're affecting how fast warming goes up. And ultimately, as I said, how high we go depends on CO2. But because these pollutants are short-lived, if we remove them from the atmosphere, if we stop putting stop putting emissions into the atmosphere, they rapidly decay, and so we can get short-term benefits in that time frame of decades. And so they're a great opportunity for us to make short-term progress while we deal with the long-term carbon problem. The good news about methane is that there are a lot of ways that we can reduce emissions today. Some research that has been done by colleagues at EDF show that about half of the methane emissions being emitted across all sectors can be reduced with available technologically achievable strategies. Half of that half, so another 25% of the emissions of methane can actually be reduced at no net cost. They're economically viable. If we were to take these actions, we would reduce the rate of warming by 30% over the next couple of decades. And ultimately, we could reduce warming by 1/4 degree Celsius by 2050. And just to give that a sort of a sense, an order of magnitude for you, we've already experienced over 1 degree of warming since pre-industrial times. The target that we've set, sort of, as a joint countries of the world, it's a target of 1.5 degrees Celsius as a stretch goal, with a 2 degree Celsius increase as the maximum. And so avoiding 1/4 degree by 2050 is a pretty big deal. And so we can do that just with methane action alone. So Michael mentioned some research that's been done to try to understand how much methane is being emitted from the oil and gas industry, which is, sort of how natural gas is delivered to our homes and businesses, sort of where from the point that we produce it to the transmission and distribution of it. And what I'm going to present is sort of draws on years of research that's been done from people going on sites, as you see in the slides on the left side of this slide, as well as going on roads, downwind of facilities, as you see in the bottom center, going on aircraft at the top center, using drones in the bottom right, and ultimately now increasingly using satellites to detect large individual sources of emissions, as well as emissions coming from like entire oil and gas production basins. The conclusion of all this work, and this is now a few years old, but in 2018, I was the lead author of a paper that summarized all the research that had been done at that time. And you can see in the bars here that the dark blue is what the research of the measurements was compared to the green, which is what the Environmental Protection Agency has in its inventory as its estimate. And you can see, especially for the production area in the left side, where most of the emissions are generated, that there was like a factor of 2 difference. Overall, it was about 60% higher emissions were being observed, in fact, than there were in the inventories. This research has been expanded upon, and invariably, whenever you go to measure emissions of methane from the oil and gas industry, the emissions are higher than what the estimates are. And so it basically underscores the importance of controlling them, as well as continuous monitoring to manage these emissions because of their implications for the climate. Among the studies that was done was leak surveys, emissions from local distribution pipelines. We partnered with Google, who outfitted their vehicles, their street view mapping vehicles with monitors to measure methane emissions. And we drove those cars with Google around cities and found individual leaks could be observed. And we developed methods to quantify, when you observe a leak, how large the emissions were. It's not a perfectly accurate method in terms of like the ability to get it to like the second or third decimal place, but we could kind of bin the emissions into like large emissions, medium emissions, and small emissions, with the large emissions being the ones that drive the overall totals. We see a lot of variability in cities. Some cities like Boston on the left side with older pipeline networks, have much greater emissions than cities like Indianapolis, which with much smaller networks. Which much newer networks and pipe materials that are more durable than some of the old steel, iron and cast iron pipes. And so this can be repeated over many cities. And now these methods of looking for leaks with mobile platforms has been an effective way to sort of quickly find leaks and sort of prioritize repairs. But the bottom line is that there's a lot of leaks that come from pipelines. And this slide is a little busy, so I'll walk you through it. There's additional methane that's coming into the air in cities that isn't just attributed to pipelines. And the cutting to the chase, the hypothesis is that there's a lot of methane that's coming from other parts of the natural gas system that are kind of like what they call behind the meter. So when the gas is delivered to your home or business, there's leaks in the pipes inside the house, or there's leaks from the appliances that we use. And so there's a lot more methane that comes from the natural gas supply than just the pipeline leaks in cities. And when you look at this from the standpoint of like what's in the inventory, the gray bars in each of these represent data for 6 different cities around the country. In the US, there's similar work that's been done in Europe and other places. Each one of the bars represents an individual study. And what you can see in every case is that the inventories in the gray bars are lower than what you get from observations, whether you're doing emissions from aircraft, from remote sensing like satellites, or from towers. The emissions are much larger in the actual atmosphere than estimated. And you can see at the top, I've summarized from this paper that the loss rates are on the order of 1% to 2% or more of the emissions of the throughput that goes through a city. So whatever the consumption of natural gas is in a city like Los Angeles, for example, 2% of the gas that's being used within LA is being emitted into the atmosphere as methane. And so significant losses, these add up, they have climate implications. And it's important that we consider these as we manage these systems and we think about what our future energy supply looks like. So that's the story from the climate standpoint. Another area that's gotten a lot of attention more recently is the air quality implications of the use of natural gas in homes. Basically what happens, with a gas stove or other gas appliances, you're basically burning the natural gas. In the process of combustion, there are other chemicals that are produced in the process, starting with nitrogen dioxide, as well as other chemicals, organic chemicals that are hazardous to health, like benzene. Nitrogen dioxide causes asthma, can lead to premature mortality. Benzene is a carcinogen, and this recent research that comes out of Stanford University, Rob Jackson's group, they've done careful measurements inside homes with gas appliances and have seen the buildup and quantified the concentrations that build up in homes because of the combustion of natural gas or propane as well. And the levels that can be reached are, at health relevant levels. These are levels that can cause public health harm using established research. And so one takeaway from this is that if you do have gas appliances in your home, it's really important to have ventilation, to use like well-functioning hoods to extract the exhaust and vent it outside, or open windows, or both. Just to make sure that these combustion byproducts are being extracted from the home and not harming health. And so this is kind of like I said, a newer observation. It affects all of us that have gas appliances, and something to consider as we think about the future. So I'm gonna shift to sort of like the larger context, like kind of the policy context for this, especially in the state of California, which is leading the country on trying to decarbonize. The goal of getting decarbonization in California by 2045 envisions that about 90% of building energy demand is going to be achieved by electrification. So on the left side, you see the light blue sections of the bar represent the use of natural gas, fossil gas, for energy in buildings. You can see by 2045, the forecast is that that's almost completely eliminated. There's a lot less overall demand from buildings, but most of it, 90%, is going to be electric. So we need to be looking at ways to reduce that fossil demand in order to achieve the climate goals. And one of the ways to do that is through building electrification. And then the questions come around about like how does a natural gas utility transition from the current climate, environment to a future environment where natural gas is being phased out. And so one of the options, and Environmental Defense Fund has done some research and advocacy around this point, is non-pipeline alternatives. So rather than adding more pipelines or adding more gas to the system, is to shift utility investments towards cleaner solutions. So instead of thinking of natural gas as a product that people consume, is like think about what people are using natural gas for example, for heating. So can we come up with alternatives for like use of electricity to sort of heat homes instead of natural gas, and sort of redesign utilities around the provision of that service. One example is the state of Vermont has authorized a utility there to earn a return on investment for a program of installing heat pumps in homes, including programs for leasing and servicing of those. And again, instead of having a natural gas pipeline system that they manage, they're now sort of providing a service that allows them to continue to earn revenues. And I provided a link to that report here. So that's kind of a really rapid tour of what we've learned about natural gas emissions and methane into the atmosphere, and especially within cities. I'll close just with this image of a methane molecule that's prominently displayed in the Netherlands, in one of the earliest places where natural gas was found in Europe, where they're almost now producing no gas at all, and transitioning into cleaner alternatives. So thank you very much for the opportunity to speak today, and happy to participate in the discussion as we go forward.
Thank you very much, Ramon. And if you'll hang around towards the end here, we'll have more questions. And there's the number that you can text those to, or if you're online watching, use the chat function on your browser to submit those questions. That was excellent on the overall picture of natural gas. Personally, having lived here 45 years, I think heat pumps are a great idea, especially in Santa Barbara. Our next speaker is Ira Leifer, who is a former researcher here at UCSB, specializing in seepages, which we're all aware of, I think, out in the channel, which are one of the largest natural gas emitters in the country. Ira? He's also CEO of Bubbleology, which is a company that looks at these kinds of things.
Among other things.
Among other things.
Okay, so let's see. Yes, Santa Barbara. So I envisioned in my mind when showing these couple of slides, you're listening to the soundtrack of Jaws. Not very helpful when you're with the divers. They don't like to hear that soundtrack, but there is a dark secret, or an elephant in the room, which is the seeps. So first, what is a seep? A seep is an area where gas or liquids, could be oil or so on, comes out of in either the earth into the atmosphere or the seabed into the ocean. And they can come from biological sources. So you can have microbes that make methane and then bubbles out. You see that in wetlands all the time, for example. Or thermogenic petroleum, and it kind of comes out through faults and fractures. What's important is there's a wide diversity. And here in Santa Barbara, we have the Coal Point Seep Field, which has from tar blobs coming up to sand seeps is like 10 or 15 feet. Ivy super seeps is about 60 feet. And these actually kind of bubble vigorously. Okay. Another key part is that to have a seepage, the gas has to accumulate, or else it'll never aggregate to then be able to seep. And there's a microbial filter right at the top of the seabed where you have microbes that use air, oxygen, and they eat that methane really well. So it doesn't get out if it comes out dissolved. So if you want to bypass this microbial filter, you need a bubble. My company is Bubbleology Research. Okay, this was going to play, but that's like about 10 feet across, and we'll just kind of go on to, oh, there it's playing. So this is out on a boat, and you can see the bubbles of methane and other gases coming up. And this is trilogy seeps. They're quite impressive, less so now than they were decades ago. But this gives you a little bit of an idea. And for me, as a seep scientist, they're the eighth wonder of the world. Okay, not everyone views that, but we say who has smelt the oil is never again free from doing seep science. The seeps extend from Coal Point, where they're only a couple of feet, right in the intertidal zone where people are surfing. The further offshore trend, the South Elwood trend, is in about 200 feet of water. And there's a geological control of this, which we're going to see in another second. The seep field is an area that's all interconnected. So this is an area where when something happens in one area, it shows up in another. Platform Holly, which is aimed to be decommissioned, in this has virtually no seepage around it. Okay. This is a photo of the trilogy seeps in 2005 when we had the exceptional rains, and this created a huge oil slick offshore, and my theory, due to aquifer recharge, just turbocharged the seepage, which you can see. This is from an airplane, so that right picture is probably about a mile from the top to the bottom. This is massive, and at that time, if you went over that bubble plume and you weren't smoking, which is a bad idea on a methane seep, not to mention the oil slick. If you went over it, the actual bubbles would literally just push the boat out of the way. 40-foot, you'd sort of like you weren't there. I remember in one of these, I wanted to get some gas samples, and I had the diver go overhead, over into the seep, and he had like a jar to try to catch some bubbles and a funnel. And his flippers were up in the air, and he couldn't get down because the water's coming up so fast. So this is why I call them a wonder. But you also can see on the lower left the close-up of that oil. And while we are talking about methane, I'm going to also bring in air pollution, which Ramon introduced. Why are the seeps where they are? It's the geology, and the pun geology rules is meant intentionally. So you can't have seepage through solid rock, because it's solid rock. Purple is the reservoir layer, the Monterey Formation. It underlies the entire channel. There is still active hydrocarbon formation going on in this layer here. In other words, in theory, if it was produced at a slow rate, and platform holly isn't, it could produce oil forever, literally. The seep field is at least 500,000 years old. It's been seeping for that long. And it comes up through these faults and fractures. And this is an important problem for California, which is seismicity, not just because it knocks down houses and causes damage, but it also means that if there's a well through a fault, well, that fault's going to move, and that well's not going to stay sealed. And this is an issue that I'm working on with Heal the Ocean in Summerlin, where some of those wells that were long abandoned are on faults, and when the fault moves, well, it reopens as well. Okay. Now, why is it in Coal Point and not, say, down in Santa Barbara? And you can see in light blue is a transect along the coast, and that Monterey Formation is shallowest in Coal Point. It's also shallow in Point Conception. And in Point Conception, it's actually thought there's more oil emissions coming out than Coal Point, but Point Conception being generally windy, generally wavy, generally a messy area to try to do research, hasn't been studied as well, and it goes off into the greater Pacific. California is blessed or cursed, depending on your point of view, with a lot of natural oil and gas resources. So there are petroleum hydrocarbon reservoirs all up and down the coast, all through the Central Valley. LA, which is there because of oil. Oil brought the people, and then the people came afterwards, and then they are now living among oil. And so this is part of the issue, that there are seeps all of these areas because it's seismically active. The ground breaks, and the oil and the gas can get out. Coal Point is one of the more expressive and larger of these sources. But this is part of the problem. There are a lot of wells dug into these reservoirs. I don't know, there's something like 30,000 that need to be abandoned, and there's something like 130,000 in the state at this point. And these are all straws from the reservoir to the atmosphere. Now, they've been sealed, more on that later. Okay. The Coal Point seep field has changed over the years. So there actually was, the contours or sonar maps of the seepage field in 2005. The outlines and the observations show prior observations of where seepage was. In the 1940s, there was way more seepage than there is now. It was much more extensive. I will note there was no seepage around Platform Holly. In the 50s, it's the same, but it shrunk. In the 1970s, it shrunk further, and this is starting to get into the question, if you produce a reservoir, you're lowering the pressure. Are you lowering also the emissions? Right. And that brings us up to date. Okay, let's see. Where does the oil go? I think, yeah. Oh, background didn't kind of show up on this. Hope it does on the next one. Yeah, okay. Who cares about seeps? Well, we're here to talk about methane, and what I'm showing here is Tripoli satellite methane for the state of California. This is 5 years aggregated This is not yet published, though I plan to submit within about a week. And so key features. The Central Valley, that's where you see the methane. Now, let me get the laser pointer, which people online. This here is Santa Barbara, and that's the seep field. Here's Ventura, here's Los Angeles. Here's the Central Valley. There's oil and gas over here, some dairy here. There's oil and gas over here near Bakersfield. There's also dairy in this area as you go further north. Now this one I think is pretty interesting. This little blob here, and let me back up for a second. This is concentration. Concentration is not emissions, right? And there's this, regulations, if the concentration is above a certain amount, we have to do something. But you have to actually know what the emissions are, because I can get really close to the leak and get a high value, but it doesn't mean anything, because if it's a small leak, I could go back away and make it small, as a matter of fact. Could create any values I want. One of the things we do in our research is we derive emissions. If the wind speed is the same everywhere in the state, which it's not, but it is within a factor of 3, then it will scale with emissions. And so this little blob here is sitting right over Trico oil and gas field. It's actually one of the larger blobs. As a matter of fact, it's kind of not that dissimilar from the entire LA basin. It was abandoned 50 years ago. You go there and you see some crops and you see some dirt and you don't see any infrastructure. It doesn't look like an oil and gas field. And yet it still kind of is showing up. I'll also note that where we have gone and validated, down in LA in the port area, here as well as in the Central Valley, our in situ measurements agree with what I see in the satellite. Now I'm going to kind of push in a little bit closer to the next one, to our neck of the woods. And the scales have been changed because the San Joaquin Valley just blows it away. And I'm going to get into something cool and then come back. Here in the Carrizo Plains, we actually have some methane coming out. And I've gone there and looking at it and collected some measurements, and I actually think that's mantle or petrogenic methane coming through the San Andreas Fault. And actually in the satellite data, I see methane coming up the San Andreas Fault in many parts of its length. It may relate to seismicity. We have helium measurements, so I know there's stuff coming up from the mantle there. This is not thermogenic, not oil and gas like dinosaur goo. This is an interesting, completely aside, but it is part of the methane emission of our natural world. So here, Colo Point, when the winds are right, they blow the methane up into our local mountains. Trapomie doesn't work over topography, so we don't see any data for the mountains, and it really doesn't work over the ocean. And then you can see these little hot spots. And most of these are sitting right above abandoned oil wells, oil fields. Abandoned many decades, even as much as 100 years ago. And they are still emitting methane. And you know what? These are not in any inventory. As a matter of fact, these are all considered non-emitters. Here we have, Santa Barbara. There's actually probably a good point to mention. Question. What's the biggest source of greenhouse gases and pollution in Santa Barbara? If anyone says, I hate LA, you're right, because it's LA air when it comes up here. The second largest source is the seep field. Here, for example, just kind of, you can see Lompoc oil field. It didn't even show up on the other scheme of the whole state, and yet at this level it does. And just to throw in one more little thing, Santa Maria, the part of Santa Maria that used to have oil has higher methane than the part of Santa Maria that doesn't have oil. I've seen this in our data. And where there's methane, there's also volatile organic hydrocarbons, air pollutants, things that cause cancer, respiratory problems, neurological problems, and they're related to the oil. So how much gas is coming out of the seep field, how much oil? I'm just re-showing this map so we can see West Campus Station over here has been downwind of the seep field since the 1990s. And I have gotten all the data from it, the total hydrocarbon, which is primarily methane. And I inversion modeled it. And since 2008, it's a perfectly beautiful exponential decrease. So back in 2008, the seep was emitting 160,000 cubic meters a day, which is higher than the public number that's been cited, but it's been decreasing since. Now, this exponential decay is exactly what you see in a produced oil field. As you produce the oil out, there's less there, less pressure, it's harder, it goes slower. The seeps are producing the oil field. The seeps are producing the methane. It follows this beautiful trend right up until right about here, and then it goes above trend. And what happened in 2015? Platform Holly was shut down. So as soon as Platform Holly was shut down, then the seepage picked up. Okay. So this is an unintended effect. Now, I've even looked at the sectors, and you can see it picks up not from where Platform Holly was, but it picks up from where the Lagolita seeps are. So it did, the gas emissions are 100,000 cubic meters per day, but also it's emitting other things. So 0.9 gigagrams of ethane comes from the seep. That's 7.5% of the entire South Coast Air Basin emissions, including LA. So that seep field is producing 1/10 the emissions of LA and all the surrounding area ethane emissions. Propane is the same thing. As a matter of fact, if the global propane numbers are right, then the seep field is producing almost 1% of the entire global propane emissions. I don't believe that. I think the numbers of the propane inventories are worse, but that still gives an idea. Butane, we're also at about a gigagram, which is again 5% of the entire South Coast Air Basin. Pentane is 0.3. Pentane is where we start getting into health effects. So pentane does cause neurological problems. Benzene was only 12 kilograms. You just don't find that much benzene in crude oil. We put it in our refineries because it keeps our engines from knocking. Benzene is a very well-known carcinogen. There also are, and I haven't yet published this is all published, a lot of other volcanic organic hydrocarbons coming off of that oil. Bottom line, it's not good stuff to breathe. Okay. We've gone out, and I'm going to go forward. So you may have seen my vehicle. It's now white, driving around Santa Barbara. So it's an air quality lab that I put in the back of the truck, but also can go on a boat. And we measure now 18 different gases, ionizing radiation. We do aerosols, profiles of aerosols. We do ultrafine aerosol size distributions. It's truly a unique capability. And this is where we took it offshore, and we were measuring the emissions from the seeps with in situ. And so this is our validation of that inversion model that I showed a little bit before in terms of the total amount. The official estimate is 100 barrels a day of oil. I have data that says it's quite a bit higher. Where does it all go? Off to China. Okay, they give us stuff and we give them oil back. Seriously though, it doesn't stay on our beaches for long. It doesn't stay in the channel for long. It keeps going. 500,000 years. 100 barrels a day means 1 Exxon Valdez every 3 years. For 500,000 years, we would have asphalt paved beaches if it stuck around. It keeps going. We'd have a tar mountain in the center of the channel if it stuck around. It doesn't, it keeps going. And this is how we can have very large oil emissions and we don't see it. Okay, moving forward, and we're kind of getting to the end. I'm going to just change into something completely different than seeps. And so I also have this company, you can see the Solaris energy trailer outside, which is designed to provide commercial level solar power for a backup as a generator to improve resiliency. And underlying this, and this is kind of one of the things that I wanted to share to kind of feed into the discussion, is this concept of resiliency. Whenever we change policies and regulations, there are a lot of impacts and implications. one of which is in the environment, and it's often required that environmental impact studies have to be done. Well, I would propose we also should do resiliency impact studies. As we move into the future, I noticed the slide on the electricity used for California, and it had to drop by 50, I forget the news, terajoules in the next 20 years or something. Like 50% of the energy usage has to decrease. Even though the population's going to go up, even though we got server farms coming in and AI coming in, and everyone wants to use more power. So this reduces resiliency. And resiliency is what keeps the power on. Again, this is aimed at businesses, the idea being, if you can't get reliable power in California, you're moving to another state. And we need businesses to stay here. We need a resilient infrastructure to support them. Okay, thank you very much.
Thank you very much, Ira. That was great. 45 years, I've seen an awful lot of seepage going on here. Thanks. Next, we're going to hear from Alilia Patronel, who is the Chief Climate and Energy Resilience Director for the City of Santa Barbara. And she's going to tell us about some of the plans going forward that the city has to address these kinds of issues. Alilia?
Hi, everyone. Alelia Parento, Sustainability and Resilience Director. You almost had it, for the City of Santa Barbara. And I'm going to talk about, there we go, how we're working on decarbonizing Santa Barbara. Part of the problem with going fourth in this, or third in the esteemed panel is that some of my stuff has already been covered, but I'm actually going to bring this back to the hyperlocal focus. So where we kicked off our decarbonization journey was when our city council in Santa Barbara voted to be carbon-free by 2035, about 10 years ahead of the state, which in our local governance terms is about tomorrow. So we're working really fast to try and figure out how we decarbonize our various GHG sources. They passed this resolution in 2019. So we have to start with looking at where our emissions come from. And very similar to the rest of the state, Santa Barbara's primary emissions come from transportation, and of those, most are from single occupancy vehicles. But that's not what we're here to talk about today. It's a different kind of gas. Another 40% come from building energy use. So we've already heard a little bit about this in Ramon's talk. Split pretty evenly between electricity and natural gas. Natural gas, we've already heard about why there's emissions associated with it, but electricity is kind of interesting. Why in a state that does not use coal do we have a lot of emissions in our electricity? Well, basically, California's on a high gas diet and has been for a lot of decades. Really interestingly, about 45% of the natural gas demand in California is used to make electricity. So that's sort of problem number one that we have to face. In Santa Barbara, we're really aligned with the state here too. 21% of natural gas use is in residential buildings. And where that goes in residential buildings is space and water heating. That's why you see a big drop-off for commercial buildings. You're not using a ton of space and water heating in commercial buildings versus lighting and air conditioning, which is usually more electricity focused. So, oh look, I even had animations. All right, so what was our step one? Clean our local grid. In Santa Barbara, our municipal load, so the load we have direct control over, is about 8% of the total load. So that was not going to get us to a decarbonized Santa Barbara. So we turned to another mechanism that was allowed in the state starting in 2002, which is community choice aggregation. Does anyone here know, raise your hand, what CC is? Of course you do, Dennis. Nobody, okay, we're gonna explain it. So community choice aggregation in Santa Barbara, we founded a CCE, and I'm going to explain what it is, but we founded a CCE, so community choice aggregation or community choice energy. We think community choice energy makes more sense to most people. We founded a city-only CCE. Most people joined together in JPAs, but at the city we wanted ultimate control of both our power content and our rate setting. So Santa Barbara Clean Energy, which you may have seen on your electricity bill, was founded in 2021. Really with the intent of a cleaner coast and better future. So community choice aggregation works as a partnership between a local jurisdiction or group of local jurisdictions and the investor-owned utility. In Santa Barbara, our investor-owned utility is Southern California Edison. I think you're all probably pretty familiar. But what happens is the CCE becomes the procurer and builder of power. So we buy and build our local content. We contract with big developers, or we really have the intention of trying to build as much of it locally as possible. The investor-owned utility, or SCE in this case, continues to deliver the power. They still own the poles and wires. That is their wheelhouse, and certainly not ours at the city. So they continue to reliably deliver the power. The consumer notices very little change. We had the unfortunate reality of launching Santa Barbara Clean Energy right as Southern California Edison rates went up 60%. So a lot of people think that SBC drove their bills up, but actually they're pretty much exactly the same. The important part of this conversation and why CCE plays such a big role is, remember, we only control 8% of the load in Santa Barbara, but CCE by law is an opt-out program. So when you form a community choice aggregator or energy program, every eligible customer is automatically opted in by law. This is the state's call, not ours. And with the option to opt out, which means that overnight, by defaulting all of our customers to carbon-free electricity, we eliminated that whole piece of the pie. So 20% overnight of our emissions were gone. That's really pretty impressive. But that wasn't the most exciting part of it. The most exciting part of it was we now had a valid pathway to decarbonizing our local emissions. Because leveraging that clean grid, we can now tackle vehicle electrification and building electrification, those biggest sources of greenhouse gas emissions in Santa Barbara. Again, vehicle electrification is a talk for another day, so I'll focus on buildings. So we have two areas of buildings we need to focus on: new buildings and existing buildings. New buildings are the easy ones to tackle because we can do it legislatively. I just wanted to show this. This is very similar to Ramon's bar graph, but this shows sort of California as the grid in California cleans up through the renewable portfolio standard. This shows the benefit of going all electric in a building. So in 2020, it was about a 50% drop-off in greenhouse gas emissions. But again, as the grid gets cleaner, that becomes better and better, with the aim in 2050 of being about 82% more or reduction in greenhouse gas emissions. However, in Santa Barbara with SBCE, we did that in 2022. So really exciting and really needing to focus on all electric buildings. So the natural gas ban. As Michael mentioned, Berkeley led the charge, with Santa Barbara coming in second on the natural gas ban. And really the whole point of it, because these types of legislative actions in California need to be proven cost-effective by the California Energy Commission, we proved that it was cost-effective because you're eliminating the cost of integrating the natural gas system to the new building from the main. This applied to all new construction as well as large redevelopments, so you didn't have to be starting from scratch for this to apply to you. And we did exempt restaurants and laboratories, even though we don't really have any in Santa Barbara, but we wanted to welcome them. And the reason we exempted restaurants was this was coming on the heels of the pandemic, and we were really trying to balance recovery and our natural gas sort of approach. So that's why we started with a restaurant exemption. We had a lot of concerns. Probably everyone in this room received a text message from a nonprofit called Californians for Balanced Energy Solutions that told you we were going to come in and rip out your gas lines. So we had a lot of concerns about what did this mean? Is the grid ready? Is it too soon? It's not too soon. In fact, 35% of homes built after 1980 in the US are already all electric. The East Coast sort of has us beat on this because of their huge amount of hydropower. And so it's a well-proven technology. Affordable housing projects throughout the Central Coast are being built all electric and doing so cost efficiently. So I'm not sure why it wouldn't be valid for other types of building developments either. Another big one that we heard that I don't actually have a slide on is, can the grid handle it? Because we're already dealing with the public safety power shutoffs, which have nothing to do with grid reliability, and also rolling blackouts. We all remember the Enron days. The electricity system is a summer peaking system. So if you're transitioning heating for space and water heating, that's typically a winter peaking system. So you're actually balancing out a lot of the demand of the two energy systems by transitioning. Also, this isn't happening overnight, so we have some time. The other really, really neat part of an all-electric home is the home can actually become a localized grid. You have heat pump water heaters, for example, that can act as energy storage, similar to a battery. You can preheat the water and use it over time, certainly if there's an outage, or just to balance your grid cost. Additionally, there's smart thermostats and smart appliances that can help you manage your cost or manage your peak demand based on when it's deploying. This is really important because you can't make natural gas at your home, but you can make electricity at your home. So all of a sudden, you have the power, literally, to control your cost and resiliency. Isn't gas cheaper? So per unit on your bill, gas is cheaper, but it turns out that all of these new modern appliances that we're pushing in home electrification are 4 to 5 times more efficient than the natural gas appliances, and over the life cycle of the appliance are substantially cheaper. The thing we're contending with is that upfront cost of that capital investment, and that's where all of these incentives like SBCE is launching, for example, heat pump water heater incentives or air source heat pump incentives that help mitigate that upfront cost. So what the ban accomplished, and this was sort of driven home to me as we were hearing Ira's talk and Ramon's talk of like, what can little Santa Barbara do? What impact can we have on this global issue? Well, I said Berkeley was first and we were second. 44 jurisdictions followed suit in California, and that's just California. Several states followed suit after California, so we have a tremendous impact by leading the charge. Additionally, we eliminated future emissions in those buildings that were built during that time that the ban was in place. When a building is built, those emissions are locked in for 30 to 50 years minimum. So we have a real responsibility to eliminate those. Additionally, we sent a market signal. When 44 jurisdictions in California transition to all electric, manufacturers start making better products. And that's a really important piece of the puzzle. And we started a conversation. People in Santa Barbara didn't know that they had a choice between dual fuel or all electric because we've always heated with gas. Now we have some options. So what happened? Michael already told you what happened, but the Ninth Circuit ruled against these bans in 2023. And so we did have to pivot. We had to pivot to something called REACH codes, which is actually how we were going to handle existing buildings, but I'm not going to go into that because my counterpart at the county, Garrett Wong, is going to tell you all about REACH codes and what's next.
Thanks, Aurelia, for setting up the stage and taking some of the hard questions that we usually get when we work on this kind of policy work. My name is Garrett Wong, and I'm the Climate Program Manager for the County of Santa Barbara. One of my main charges is implementing the county's 2030 Climate Action Plan, which was recently adopted a few weeks ago. And so similarly as the city of Santa Barbara had adopted its natural gas ban, the county of Santa Barbara was also working on a similar policy, about 1.5 years behind, but it was right around the time in which the Berkeley decision was starting to unfold, and then ultimately it came to its final conclusion. So that meant we had to figure out, well, what is the next best alternative that we could turn to when it comes to what Aurelia had mentioned as the objective of limiting future natural gas emissions in the built environment. So, as I mentioned, our 2030 Climate Action Plan was adopted last month, and one of our actions is to adopt and implement a policy that would affect new construction. So similar to the city, we also have greenhouse gas inventories, but being the county, it's a lot more varied and diverse in terms of where our emissions come from. We have agriculture, we have oil, we have industry. We also have a lot of off-road activity in the county, but natural gas still features fairly large as its own source of emissions, and so limiting, reducing natural gas emissions is still a top priority for us. So, Aurelia mentioned briefly what is a REACH code. How did your little leaf logo end up there? I don't know. But an energy reach code is a little bit different. It functions differently than the natural gas bans. And the natural gas ban is very direct, it's very upfront. You know what is allowed and what's not allowed right before you come to the counter, permit counter, and you're basically saying, well, this is my options, and I might have the opportunity to exempt my project, but by and large, you're subject to the ruling. Energy reach codes are different. They're enforced through the energy code and the Title 24 modeling that's done for a building, and so it becomes an engineering game to comply. Because it's a part of the energy code, the California Energy Commission is involved. They want to make sure that policies that are adopted at the local level are deemed cost-effective. So anything that has a premium in terms of the upfront cost, that the lifetime of that equipment or the lifetime of that improvement actually save more money than that premium. So functionally, natural gas is still allowed under the state's code and will still continue to be allowed in the upcoming code. But REACH codes allow for local governments to set higher standards in terms of energy performance. So on the diagram here, we have an example, just a conceptual one, showing two different buildings as they would be kind of modeled and evaluating their energy performance. So the left-hand side is the electric code, or electric building. The right-hand side is the natural gas and electric building. But if we move up in the chart, that would be higher energy performance as the code considers it. So the state has kind of a minimum standard of what energy performance is, and both electric as well as a dual fuel building can meet that code. But a local government can establish a higher standard of energy performance, which an all-electric building could still easily meet if it was built to code. But a natural gas building would have to include additional energy measures, such as increasing energy efficiency, increasing solar energy, or potentially a battery storage system to help compensate for the natural gas impact of that building. Bottom line is that we're getting better performing buildings at the end of the day. Natural gas is still allowed, but again, the impacts of that natural gas is being offset by greater energy performance. So this is getting a little bit into the weeds, but the county has been working on building policy for the past couple of years, first with the natural gas ban, but now pivoting to the REACH code. So we're trying to kind of hold what we've done before in our stakeholder engagement process and working with different constituents and different industries to acknowledge the variability, the differences, the challenges that they face when it comes to designing and constructing buildings. We're trying to work with the cities of Santa Barbara, Carpinteria, and Goleta to develop policies that are fairly similar, so there's some regional consistency, although how we apply them will always usually be different. And so our current, we actually just went to the board earlier this week on Tuesday to give them kind of a similar presentation, update them on what's transpired since the Berkeley decision, provide a little bit of education on what is a REACH code and how the county would go about doing that and how it might be developed and implemented. So the board did approve us moving forward with that, so we will be continuing to work with the cities and other stakeholders to develop that policy and move it towards adoption. So Valilia touched on a few of the maybe myths or maybe kind of misconceptions about going all electric, and one of them is that it's more expensive. A lot of that is probably associated with the fact that a lot of new buildings are being built as all electric. New homes and buildings are just generally more expensive. So that's also part of the thing, discussion. But there's a lot of incentives. There's a lot of incentives, a lot of programs, a lot of people who are interested in seeing all electric construction, as well as all electric buildings, buildings that are already existing to be transitioned to all electric. So there's a wealth of programming and resources and more resources that are still coming online. And so it does take a savvy customer to kind of understand the network of all the constellation, I would say, of all these different programs. But if you play your cards right, and if you make sure you're applying to the right programs, you could essentially get a zero upfront cost piece of equipment that would get you closer to becoming a zero emission home or zero emission building. Some of the availability, some of the limits, some of the funding amounts are slightly different. This was done a couple years ago. But looking at a single-family home, we also are looking at the incentives that are available for a multifamily, which are slightly different, but still significantly cutting down the upfront costs. And then when you look at like electric vehicle electrification, we also looked at what's available. Again, these are changing, but a lot of the programs are still available. So in the end, where are we going? Well, we're hoping to transition our communities to be more carbon-free, functioning on sources of renewable energy, sources that are carbon-free. And if you couple both electrification in the home as well as in the vehicle, all in all, the total cost of living should come down. The energy burden is what we call the amount of money people have to pay as a percentage of their income to energy-related utility bills, gas bills, and the like. And Southern California Edison has done some studies and looking at to the future, and they're looking at their rates, looking at other rates of natural gas and comparing, and vehicle fuel, comparing in the future, where are these trends likely to go? If you're going all electric, you have a little bit more control of your energy destiny and your energy burden. And being able to reduce that on whole should be realized if you're able to achieve electrification in both. Thank you for the opportunity to speak. I look forward to the discussion and the questions.
Thank you, Garrett. And thank you, Alita Parenteau, right? Did I get that right that time? Okay, my apologies. Next, we're going to go up to Stanford University and hear from a speaker whose area of interest and expertise is energy economics, and talk about a little bit about the different choices and what the costs may be that involve that. This is Frank Wolak from the Stanford School of Economics.
Thank you. So what I'd like to talk about is basically what I would say is, as an economist, my view is that it's best to just give decision makers an understanding of the trade-offs they face. And so what I'm really, since effectively every public policy decision I've ever seen involves benefits and costs to different groups. If all groups and all things got benefits, then I think the public policy decision-making process would be quite simple, but that is rarely, I've never seen such a case. So what I wanted to first do is just present some data on fossil fuel consumption, CO2 emissions by country for places like China, India, Germany, UK, US, and look at also by fuel source and consumption as well. And then dig into some data from California on its in-state generation mix and generation mix of the remainder of the Western Electricity Coordinating Council, which is essentially the Western interconnection, where effectively California gets roughly 30% of its grid-supplied electricity currently. Roughly 30% flows in over from regions in this green area here, which is the Western interconnection, which is an interconnected grid that serves this entire region. So potentially any generation unit that's operating in there could potentially be delivering, or the electrons are injected to the AC grid. Okay, so this is annual CO2 emissions by country. And as you can see, that is probably well known, is that China is skyrocketing, yet the United States is increasing slowly till roughly about 2005, 2006, and then it starts to decline. India looks very much like China in the sense that continuous growth in greenhouse gas emissions, although not as rapid. Germany starts higher than, say, the United Kingdom and slowly declines. The United Kingdom pretty much starts low and declines as well. So, these are the stylized facts that I think we want to dig into and try to understand what's going on. The way we'll do that is just look at fossil fuel consumption by fuel source in each of the countries. So the first and the easiest way to do it is just standardize from one unit of measure. It could be BTUs or it could be kilowatt hours. There's an equivalence between the two. This is essentially annual fossil fuel consumption for China. And the important thing to see is pretty much it's coal and increasingly so coal. Oil is primarily, used in transportation and other kinds of things, and then a little bit of natural gas, but very, very small amounts of natural gas are consumed in China. India, again, looks very much like China in the sense that very rapid increases in coal and not much increase in gas. So, the last point that I want to make on here is just the fact that China and India are the major coal consumers globally. And the interesting thing though is if you take a look, you can see this graph of what it looked in the United States coal consumption right around that same time that you saw greenhouse gas emissions reducing in the United States. You see coal consumption in the United States declining, and similarly with Germany, you see coal consumption declining. And in the case of the United Kingdom, coal consumption virtually declines to zero. As wrote right here, China is very definitely the world's largest coal consumer by a wide margin, and ever increasingly so, primarily in the electricity sector, largely because it does have a lot of domestic coal resources. Germany there's been a decline in the amount of coal consumed in Germany, but they still consume a non-zero amount and have effectively built a couple coal-fired units in the past 15 years. So in the case of the United Kingdom, the so-called dash for gas, North Sea gas, in the 1990s essentially led to most of the utility generators in the UK to switch away from coal, very old coal-fired units, to natural gas units, largely by the fact that gas was quite a bit cheaper. And then the interesting thing in the United States is this rapid decline in US coal consumption, and that's what we want to dig into a little bit. So what you can see in Germany is exactly the fact that the green line, but coal is still holding, even currently, there's still a significant amount of coal consumption in Germany, in spite of the very aggressive renewables policies that they have, and the fact that they are located right next to France, which has quite a bit of nuclear power that is routinely exported to Germany. In the case of the United Kingdom, you can see this rapid decline in coal consumption during this period here, the increase in natural gas consumption with the dash to gas. There has been quite a bit of investment in renewables, particularly in Scotland and other places with wind, and the other is large interconnectors with countries like Norway and the Nordic countries, with Denmark, with the continent, et cetera. So a lot of imports in the United Kingdom. The United States is a very similar pattern in that oil is primarily not used at all to produce very little, if any, electricity, primarily for transportation. But as you can see, natural gas continues to grow and coal continues to decline. And so that's the basic story as to why it's happening. Why is it happening? It's because of unconventional natural gas. This is, for those that are following the presidential debates, is fracking, but you could say horizontal drilling and hydraulic fracturing, essentially to extract natural gas from the shale, the rich shale, a conventional gas or associated gas and coal-based methane or other ways that we can potentially extract natural gas or the major constituent, which is methane. And there's been just an enormous boom in this activity in the United States. This is just a picture of all the major what are called shale gas plays. And as you can see, even California has a few, and little activity there. The big ones are the Bakken, the Marcellus, the Barnett, and the Eagle Ford, and all the ones in Texas. This just shows the explosive growth in natural gas production from this sort of technology that's occurred since roughly almost the past 20 years. And why is this sort of what's happening? Well, what's happening is the fact that if you burn if you burn natural gas in a combustion turbine or a combined cycle generation unit, you're typically going to get roughly a third to half of the CO2 emissions per megawatt hour of electricity produced relative to what you would get per megawatt hour from a coal-fired power plant. And in addition, most of the coal-fired power plants in the United States are significantly older, have a significantly older technology, therefore are sort of less efficient in the sense that produce more greenhouse gas emissions. In the transportation sector, things like CNG or LNG transportation vehicles also produce less emissions per mile. And then again, you get rid of this SO2 and mercury emissions. And one of the big things is there certainly is ample global supply of natural gas. And if you think about unconventional sources such as shale gas, there really is, you could almost say it's quite a lot. So how does this work? Why is it that we're now finding this, switch from natural gas to coal? Well, it's primarily driven by two factors. It's this shale gas, which is driving down the price of natural gas, and the fact that you access a much more efficient technology to convert the BTUs of natural gas into megawatt hours of electricity through a combined cycle gas turbine facility versus a steam turbine facility that might be using coal. And I just go through an example that essentially shows that, look, the coal can even be cheaper on a $1 per million BTU basis, but its variable cost is going to be more than would be the case if you were burning more expensive in terms of $1 per BTU natural gas. And moreover, the capacity cost for a coal-fired unit is typically greater than that for the natural gas-fired unit. So economics is simply just driving this switch, particularly in the United States and in Europe, into investments in natural gas-fired units and away from coal-fired units, and pushing this significant reduction in global greenhouse gas emissions. So the big problem, though, is spreading this to the rest of the world, so that, if China and India, is at the bottom of the sheet here shows, is that they currently have very little, if any, natural gas-fired generation capacity, and coal for both national energy security reasons, as well as just the fact that they have lots of coal resources and very little conventional gas resources, and have developed very little unconventional gas resources, continue to effectively use coal. But in the case of the United States and Western Europe, there's been quite a bit, as you could see, switching from coal to natural gas, with the accompanying reduction in global CO2 emissions. So the last bit is just to try to hone in on California, and just to show that this is essentially taken from CEC data, California Energy Commission data. What it's showing is how much energy are we producing each year from the various sources. And what you can see is this large sort of, I guess on my screen, brown area is the amount of generation from natural gas generation units. This is just in-state generation. And as you can see here, this area here where my mouse is essentially nuclear, and this drop down is the retirement of the San Onofre nuclear generating facility, which necessitated, significantly more, and here is where we also brought in some solar, as well as some wind. But the lines that I've drawn here, the red dotted line, the height of which is the amount of natural gas generation in 2023, there are a number of years that you can go back in the past and essentially have less natural gas-fired generation and therefore less associated greenhouse gas emissions, simply because of the fact that you've got the nuclear units that are available in California. So again, trade-offs in terms of the retirement of the nuclear versus the need to have significantly more natural gas generation to essentially fill in during the times when the wind and solar, as well as the hydro, are not available. The other is that I said California relies on imports for a significant fraction, roughly 30% of its electricity is through net imports. Again, this is from the latest California Energy Commission data, is where that fraction comes from. But what you can see is outside the state, there is a significant amount of coal-fired generation capacity, which means that effectively the annual average carbon intensity of electricity produced outside of California is larger than the annual average carbon intensity produced inside California. And California is getting roughly, as I said, 30% of electricity from these resources located outside the state. So just the last bit is just to say that, yes, it is true that natural gas certainly produces greenhouse gas emissions when it's emitted, and that methane is certainly a global pollutant, but it is also the thing that is the primary constituent, as more than 95% in natural gas. So effectively, this is just this last is to show for U.S. electricity generation by source. You can see that the real major contributor to the reduction in greenhouse gases in the United States is certainly this coal to natural gas switching. And I think that in that sense, that to the extent that that would be things that could occur in other parts of the world, in particular China and India, could make major contributions to reducing global greenhouse gas emissions, at least in the time that we're transitioning. Is this possible? Well, this is just some data taken from the Energy Information Administration that essentially says that these unconventional sort of shale gas basins exist in other parts of the world. They, are likely to be a bit more difficult, but there's a tremendous amount of activity attempting to harvest these things, and hopefully, therefore, displacing coal with natural gas-fired generation. So just to finish up is that unconventional natural gas has certainly been the most impactful, energy sector in the U.S. innovation of the past 25 years. Just to give an example, today's Henry Hub natural gas price is about $2.30 per million BTU. And if you convert today's West Texas Intermediate price, WTI, which is $70 a barrel, with the sort of rough, conversion factor of about 6 MMBTU per barrel, what you get is quite a differential. So, things like switching from gasoline to natural gas in the transportation sector, can deliver a significant amount of benefits. And the other that's even just to put a finer point on it is, in certain parts of Texas and other parts, that what's happening is this gas is getting produced at such a rate, and the pipeline infrastructure is constrained, so that it's essentially individuals being paid to take it away. The other thing is that even though the United States is reducing its coal consumption, it's also rapidly increasing its coal exports, and so effectively, this is really, I think, making it more imperative that, look, it would be significantly better in terms of reducing greenhouse gases to switch from coal consumption to natural gas consumption in those parts of the world where it is essentially, the case that there don't currently exist natural gas-fired generation units, in particular China, India, and Africa as well, are all places where that switch could really deliver some significant greenhouse gas emission savings. Okay, Thank you.
Very much, Frank. I'd like to again remind our participants if they can hang around to the end. We will have questions. We've got those coming in right now. And for our last speaker, this is someone I've known for quite a long time. I first met him when we started Novum. And at that time, Stephen was the chief scientist for British Petroleum in London. Steve's background is he was provost at Caltech, went over to London for BP for 6 years, came back for the Obama administration to be the Undersecretary for Science at the Department of Energy, where he ran all the national labs and looked at alternative fuels and things of that sort. Steve is now a senior fellow at the Hoover Institution at Stanford and joins us to kind of give an overview of energy and wind things up for the day. Stephen, are you there?
Yes, can you hear me? What I'm going to do, by the way, is to try to zoom out a bit even further than Frank did and talk about global issues and longer term than what we've been hearing from other speakers. So it is true that the globe has warmed by about 1.3 degrees since 1900, and that part of that warming, at least, is due to the accumulation of greenhouse gases, mostly carbon dioxide, and mostly from the burning of fossil fuels. And many people look at these two graphs and say, shouldn't we transition our energy system to avoid this kind of human influence on the climate? So you can get a sense of what needs to be done. The world has been focusing in on taking emissions to net zero by 2050, to quote the exact phraseology, to avoid the worst effects of climate change. The graph on the left shows the steady growth of greenhouse gas emissions since 1970. Methane, which is what we're talking about today, is this purple bar over here. And what would be required to get to net zero by 2050, let's say, is this kind of decrease in the emissions from where we are now over the next 30 years or so. Of course, if the decrease is slower, then the temperature goes up a bit more. This kind of discussion and these graphs have motivated tremendous enthusiasm for making a transition in the global energy system to reduce emissions. However, in the last couple years, things have changed somewhat, and I like to use this picture to describe the energy transition today. Namely, Wile E. Coyote has suddenly realized that there are some fundamental circumstances that spell a very bad end for what he's about. What are those circumstances? For the energy system, it's that whatever we do about greenhouse gas emissions have to strike a balance. On one side, we have climate science, the risks and benefits of a changing climate, the local environmental impacts that we've been discussing earlier today. On the other side, we have the world's growing demand for energy and the technical and economic realities of providing reliable, affordable, and clean energy. And in striking that balance, we've got to fold in our values and priorities, our tolerance for risk, equities among generations and countries, and of course, the effectiveness and the costs of whatever it is we decide to do. So let me talk about some of the realities of energy transitions that have to be considered as we strike this balance. The first is that we are going to see strong growth in global energy demand, driven primarily by development, to a lesser extent by population, and to some extent by technology. Most of the action in that growth in demand is in the 4 billion people, roughly half the world, in the developing world. This graph is one of the most powerful and iconic in the energy business. It shows annual energy consumption per capita plotted against GDP per capita in constant dollars. And it's clear everything goes up and to the right, meaning as people are richer, they use more energy, or they are richer because they use more energy. The US is up here somewhere, most of Europe is over here, and what is sobering is that 50% of the globe lives down in this left-hand corner of the graph at less than $10,000 income per capita. It's difficult for those of us who live in the developed world to really understand what energy poverty means. It means indoor cooking with wood and dung. And I can tell you that these people would be delighted to have the indoor pollution claimed from natural gas or from propane. Similarly, it means lack of electricity and studying by candlelight. Quantitatively, the US per capita energy consumption is 30 times that of Nigeria, and about 3 billion people in the world use less electricity every year than the average US refrigerator. And so if we project energy consumption going forward to mid-century, we can expect, and in fact, we should hope that it will go up. This projection shows that we will go up by about 50% from where we are currently, most of that growth in Asia, which is, of course, where most of the people are. The second reality is that energy is not delivered by technologies, but by essential systems. And those systems are recalcitrant to change. They're very difficult to make changes in. Suddenly, it takes decades. And attempts to accelerate changes in energy systems can engender backlash. Just ask the people in Germany or in the UK or in Holland how happy they have been by the changes accelerated in their energy systems. Here is the US source of energy since 1950, and you can see that, as Frank was describing, coal has, coal is the gray band, has grown and then has been coming down because of the growth in natural gas, the orange bars here, and also somewhat not shown on this graph because it's not recent enough, growth in wind generation as well. But the lesson here is that it takes decades to change, and almost always any new energy source comes on top of and not a displacement for existing energy sources. If we look globally, fossil fuels have and continue to dominate the global energy supply. Oil, coal, and gas make up more than 80% of the world's energy. Wind and solar are these tiny wedges opening up in recent years. The world has spent $12 trillion in the 9 years ending in 2023 to try to deploy more wind and solar renewable energy, and the impact of it is what you can see on this graph. Another reality is that reliable and affordable comes before clean, and the great bulk of humanity, which needs more energy, is going to be looking for reliable and affordable and locally clean energy, and greenhouse gas emissions naturally take a second or third seat in how they think about their energy supply. Another important point is that a meaningful transition, namely one that can make a difference in human influences, requires scale. Governments cannot subsidize to scale. Someone has to make money. In the costs that Garrett showed, claiming that the electric lifestyle will be cheaper than the current lifestyle, there were healthy subsidies or incentives from state and federal government. Those incentives cannot grow to embrace everybody, nor should they persist forever. Somebody is going to pay for it, whether it's future generations or the deficit in the current budgets. A couple of other points, and then we'll get down to California specifically. Emissions-light energy systems currently cost more money. They carry a green premium. Wind and solar are not without their drawbacks. They use a lot of land, they use a lot of critical materials, which have to be imported currently, and most importantly, as I'll show you in a bit, their intermittency. You cannot build a grid solely on wind and solar. You must pay for the reliability when the wind and solar are not there, and it is that reliability that dominates the cost of such a grid. Finally, the green transition offers little direct benefits to consumers. Decarbonization benefits are vague, they're distant, uncertain, and we can go into why they're likely small, while the decarbonization disbenefits, costs, disruption, are certain, immediate, and likely larger. One of the things that concerns me as you talk about the Santa Barbara situation is excessively relying on an increasingly expensive and increasingly unstable electrical grid. Let me talk about the expense of the grid. This shows for the current year the average retail price of electricity by state. And you can see that California is second only to Hawaii in the cost of electricity, which is what you all want to run everything, transportation, building heat, and so on. And unfortunately, that cost is going up. This shows the cost of California electricity over the last 10 years, and you can see it's going up. I would love to see what Southern California Edison or PG&E projects for the rate over the next 10 or 12 years as we electrify vehicles, as we put in more heat pumps, as we grow data centers. Finally, gas is not going to be there gas is going to be there for a long time. This is the generation for the last 30 days in California, and it's real interesting. You see the solar, which is, of course, the yellow, going up and down every day and generating, that's great. Doesn't generate at night, of course. You can see the imports, which is the gray, going up and down. Nuclear is the red, hydro contributing a little bit. But look at the gas, which is this blue curve. It's really important, for example, during these days around September 6th, when there was a heat wave in Los Angeles. And so when you need more electricity, if the wind and sun aren't producing or there's a higher demand on the grid, you fire up the gas. You can say, well, batteries are going to fix that. The answer is you're going to spend a lot of money and take a long time to build enough batteries in California to replace this. You just have to talk to utilities and get them to have an honest, non-public discussion to understand that. Finally, a word about reliability in the grid. Nationally, we are seeing a strong growth in unusual occurrences, major disturbances, due to the fact that we're integrating more intermittent renewables into the grid. In California, we're seeing the outages increase as well. So I would feel very uncomfortable if I were living in an all-electric house with an electric vehicle. I'd be happier if I had that propane tank next to my house with a generator. Finally, quantitative. I'm a physicist by training. I love to do numbers. Let's put the Santa Barbara emissions in context. Global emissions are 57 billion tons of carbon dioxide equivalent. The US is 6 billion tons a year, which is about 11% of global. California is 400 million tons a year, or about 7% of the US, or less than 1% of global. Santa Barbara is 1.5 million tons, which is 0.4% of California, which is 25 millionths of global emissions. So let's suppose that Santa Barbara fulfilled its plan for climate action and went to net zero by 2035. It would have no direct effect on the climate. It would be costly, and it will be disruptive. But Santa Barbara could claim to be leading the world in the fight against climate change. And my question is, would the rest of the world follow? I don't know, but it's something to think about as you try to weigh that balance that I discussed at the beginning. Thanks for your attention.
Thank you, Steve. That was our last speaker, and we're going to go on to some questions, which we've got quite a few of already, but hopefully you can hang around. But before we do, I'd like to thank some of the people to make this possible. My partner, Jim Knight, Mike Rattray, Randy Rouse, the mayor of Santa Barbara, and the whole team out there that helped support this. I really do appreciate it very much. Okay, it's 11:42. I'd like to wind this thing up by noon if we could, so we could all go to lunch. But there were some good questions here. Ramon, if you're still with us after all those talks, if the least emitting source of natural gas is the United States, wouldn't it be better globally to produce it here and export it to the rest of the world where it's needed?
Well, I think it's a good question, but I think it's important to recognize the limitations of the transportability of energy, right? You have fuels that you can use to generate power, electricity, or drive a car. So coal and natural gas, for example, can be transported. We heard about exports of coal going up in the U.S. So you can produce energy sources and transport them, but obviously that generates additional emissions burdens, climate impacts, air quality impacts. And so I think we do need to have an integrated strategy that looks across, all borders, right, to ensure that we can get clean, affordable, reliable energy to everybody in the world in the most sort of climate friendly, air quality friendly, health friendly way. And so I think, we just need to be building the systems to do that most efficiently and cleanly.
I think part of the question too, Ramon, was would this be important for developing countries, which are burning coal now, or wood or dung, as Stephen said? Would this be something that would be an appropriate thing to do for those kinds of developing countries?
Well, again, I think it's a question of looking at the full footprint of the particular energy system. So starting from the production of the energy source, the transportation of the energy source, and the use. Each of those is going to have emissions associated with it, costs associated with it, and we just need to develop systems that are optimal for providing energy at the minimal climate and health impact. And we have to consider that we have to reduce dramatically the externalities of each unit of energy by significant amounts. Externalities, I mean, like the greenhouse gas emissions of natural gas, the methane leakage. If you're going to use other fuels like hydrogen as a low carbon fuel, well, you have to produce hydrogen with something. If you use natural gas to produce it, you still carry that burden of the natural gas. Then you have to transport the hydrogen. And so in theory, yes, we can transport energy around the world, but ideally we would generate resources closer to the source, especially using renewable energy with suitable types of backup power that are clean. I think natural gas as a backup power source, as was noted in the last presentation, we use natural gas right now a lot in California on peak days. We just need to be using natural gas with carbon capture and sequestration so that the net climate impact can be reduced dramatically, by 90% or more with the ideal systems.
We especially want to help out China with all that coal, right? Right, exactly. Ira, this one's for you. Were there measurable differences between the seeps during Platform Holly's production and since it has been shut down?
So Platform Holly originally never had seepage around it. And then when Platform Holly was put in, seepage became around it. And then about 20 years later, due to reduction of pressure, that seepage went away. So there's some confusion in the literature on this. It didn't take the bigger perspective. And now there's no seepage from the Platform Holly area, which was never a preferred area from seepage. Seepage wants to take up to the shallowest point it can in the reservoir. It's kind of easier. And then it goes through whatever's holding it, the Sisquoc, to the surface. That's the La Goleta seep area. So the seepage has changed. Platform Holly went subhydrostatic, and they had to pressurize it to get it to work.
I remember when the dome was put into place. Can you talk a little bit about that? Was that effective at all?
They were very effective in that they captured methane, which was piped on shore, and produced a huge pollution credit for a coal plant in Ohio, which helped Veneco's bottom line, so this was very effective. I also want to just toss in Steve Koonen's last thing, he pointed out, what is the Santa Barbara CO2 equivalent emissions? The seep field is about the same as that, okay? And that seep field emission, and that's only the seep field, not the Conception seep field, not many of the others, not Ojai, and not all the terrestrial stuff, will continue forever. And by forever, I mean millions and millions and tens of millions of years. So again, on to his point, and this is where I think what we're trying to do here in Santa Barbara with the government is very important for resiliency, because the grid is getting less stable. In terms of greenhouse warming, we just shipped our industry to China, and they're burning coal. And that happened in 2005, and so on. There's a lot of exporting of pollution. It may make us feel better, but the global climate, the globe doesn't care where the CO2 or methane molecule comes out. It's all the same atmosphere, and we're all in it together. Sorry for the little monotribe there.
That's quite all right. Alelia, this is for you. What are the current incentives to install rooftop solar if we're going to generate more power for the state of California?
Yeah, thank you. So the federal government has a really substantial incentive, the investment tax credit, which has historically been between 22 and 26%, is now 30% on the solar battery system and related work to your home, including the panel upgrade if you need it. And then additionally, locally, there are incentives. Garrett had a few on his slides from CCA companies like 3CE, or Central Coast Community Energy, and Santa Barbara Clean Energy. And because the affordability piece that was brought up a number of times is so critical to managing this transition, right? We want to bring everybody along equally. We work on a lot of turnkey programs to try to really stabilize the rates through the addition of solar and battery storage. I think that the last speaker's point is well taken, that we have, especially when our heat waves arrive, we have some serious volatility and need for that base load generation. I disagree wholeheartedly about the role of batteries, though.
Okay, thank you. Garrett, if all of these programs are more cost-effective or cheaper, why do we need regulations to require these things? What is the reason for reluctance on the part of consumers, do you think?
What is the reason for reluctance?
Reluctance on the part of consumers. They just want to pay more.
Right. So I think there's a number of different factors. I kind of boil it down to cost, convenience, and comfort. So people, again, there's a perception that there's a higher cost both to buy something as well as to use it. There's the convenience factor. Sometimes when you're transitioning from what you used to be familiar with to a new technology, there's a transaction of cost there that is either, changing up your infrastructure, beefing up your electrical system. So those are transaction costs that kind of also eat into the convenience factor. And then finally, there's the comfort. So it could be comfort, like people feel like maybe they're not going to get as much hot water from a heat pump water heater, or that they can't do the same kind of cooking that they're used to on an electric stove. So there's a lot of different factors. Some are perceived, some are real, and we, from the local government, are doing our best to overcome those challenges. Obviously, doing a lot of education, promoting a lot of the incentives and resources, and then trying to highlight where these technologies have been implemented and people aren't dying as a result of it. So,
Right.
and then there's layered on top of that are just kind of philosophical and political beliefs that this is something that the government shouldn't be doing.
Rugged individuals.
What's that?
Rugged individuals.
Sure.
We'll do it ourselves, right?
And then, people, like, this isn't the role of the government, or people should be free to choose. But I think, kind of where the last presentation ended off is, why do this, right? And I think the challenge is that when we talk about some of the policy and some of the planning work that we do, it's done in a little bit of isolation, because we talk about what's the trade-off between going all electric versus staying with natural gas, right? That's a little bit kind of a siloed conversation, because it needs to be brought into, well, what's the alternative to not doing something about climate change, which is more climate change. So, if we're comfortable with more climate change, I would want to hear that from the community to say we want more heat waves, we want more wildfires, we're good on debris flows, bring it on. Let's all sit back and not do anything about it. And so I think, where does that leave us as a local government who's supposed to be in charge of managing both the current state of affairs, but also looking forward into the future and trying to envision what does our community look like responding to climate change, avoiding the worst of climate change, and helping our communities transition along the way.
Thank you very much, Garrett. Frank, this one's for you. What is your opinion of expanding nuclear through small modular reactors, similar to what Bill Gates is proposing in Kemmer, Wyoming?
Well, I think given what we've seen with the fact that energy demand is just going to keep going up, and it's pretty low carbon source of energy, I think all of the above strategy is a good idea. One of the other things that I could certainly comment on is that one of the success stories in the United States is the fact that nuclear units that are owned in the United States have over the past decade have become far more reliable, produce far more electricity. So, given the electricity demand, and if we want to electrify the vehicle fleet, if we want to electrify some activities, it seems like that's not a bad idea.
Okay. Steve, I'll let you close out the last one here. I know when you came over as a part of the Obama administration, one of the things that the president said was, to solve the climate problem, we need to do all of the above. Can you comment on that?
Well, we do need to do all of the above. At the same time as both trying to solve the trilemma of affordable, reliable, and clean. Things that have not been discussed here that I would put on the list beyond small modular nuclear reactors is underground coal gasification. It is possible to extract the energy from deep coal seams, capture the CO2 produced, and then put it back under the ground. So that's a very interesting technology with application to India, Malaysia, China, obviously. Look, the world is going to need energy and a lot more of it. And that is, I think, the primary imperative for society. Reducing greenhouse gas emissions would be nice, but most of the world would put that in second or third place. What we can do that can be effective in the developed world is to develop and demonstrate emissions-light technologies, of which small modular reactors are one example. Certainly improve battery technology, though I think there are limits there. That's what we need to be doing. Doing ineffective small things is more damaging in some ways than doing nothing at all, because doing things will be disruptive and expensive on a local scale.
Excellent. And we'll wind this up with one more for both our city and county people. How does the city and county of Santa Barbara take into consideration the full financial costs of a shift from natural gas, not just the immediate costs to citizens,
but also the cost of subsidies to citizens to support the transition?
Great question. I think we are really doing what Garrett explained and trying to balance that future cost, right? We have very good data on what climate change is costing us now based on the debris flow and wildfire response, based on the flooding we've had the last 2 winters, based on infrastructure costs related to resiliency. This is hard data. We can argue how much of it is related concretely to climate change, but as we've seen on several graphs during this presentation, it is no secret that climate change is here. And so we are balancing that cost, but we are also really looking, as I said before, to bring our community members along on an equal footing, right? Looking at our most disadvantaged community members who are typically the hardest hit by the impacts of climate change and making sure that they are not making a decision between feeding their families, heating their homes, and getting to work. So we are allocating resources in a way to do that. We are being very proactive and working with our state and federal governments to make sure resources get to our communities and get to where they're needed most. And then being really diligent about how we're applying these technologies, right? We're really trying not to do what Steve said and really create a disruption or a hardship on anyone. We're actually trying to facilitate energy independence in a way that moves us away from this archaic grid.
I think what's challenging in our work at the local level is that we're obviously not in control of everything, right? We track what we can track. We track what we can track, we regulate what we can regulate, and then we incentivize what we can incentivize. And in the city's case, they have a little bit more dominion over electric rates. So I think that affords them with a greater control of their destiny, but we're all beholden to the utilities and the electric rates that they want to charge our constituents. And the Public Utilities Commission, I feel like, is somewhat captured by the utilities and whatever they say they need in terms of rate of return and the added, the increasing costs, but they are in conflict, I think, with where the state wants to go ultimately with reducing climate change and reducing carbon emissions. And so I think something does need to change. Hopefully it doesn't break before that change comes, but there is going to be a harder transition. It depends on who that happens, right? Is it going to be the utilities that are going to be forced to do some utility rate reform, or is it the customers that are going to have to bear the brunt of increasing costs without any end in sight? And so we, as county and city governments, we participate, we try to advocate on behalf of our constituents that affordability needs to be prioritized along with reliability, along with clean, and that local governments need to be a part of this process when it comes to rate design and program design, because ultimately we're usually the face for a lot of what's happening kind of at the state or the federal level that filters down into the communities. We're trying to share the information, disseminate the resources, and just let people know. And so sometimes we're the bearers of bad news, but sometimes we get to bring positive resources for people. And all in all, we're trying to kind of navigate how do we do this, and I think we're all in the forefront of doing this, right? We're kind of entering into spaces that we haven't been before. And so I think that's something to keep in mind, is that we're all human and working on this, and it will continue to be challenging. It won't be perfect. But again, we're all trying to work and do what we can with what we have.
I think that is a good place to leave this. Well said. Okay, I'd like to remind everyone that's watching out there were some questions about would the slides be available from the speakers. They will all be part of the recording of this session that will be available on the Novum website, www.novim.org. And it'll probably take us a few days to get them up there, but they'll be there. Thank you all for participating, those both remotely and here. It's noon, time for lunch. Thank you.